Hello statistics students, my name is Jamie Emigh. In this video we'll start our discussion for chapter 4 on probability. Let's start by expressing the indicated degree of likelihood as a probability value. Okay, so we're given a statement that says there is a 40% chance of rain tomorrow. This statement was given to us as a percentage, and what we are being tasked with is rewriting that percentage as a probability. And we haven't discussed the requirements for this yet, but let's see if we can just guess which one we think it might be. 40%, do you think that means probability of 40, probability of 0.6, probability of 0.4, or probability of 4? If you said that 40% is the same thing as the probability of 0.40, then you got it right. If you didn't, that's okay. Now we'll learn about it. 40%, its corresponding probability is equal to its decimal. 4.1 is on the basic concepts of probability. We are always going to express probabilities as fractions or decimals, not as percentages. All probabilities are between 0 and 1 inclusive. So the probability of simple event A, that's how you read this in the middle, is between 0 and 1, and inclusive means that it could be 0 or 1. That's why we have these bars underneath the inequality symbols. The probability of an impossible event is 0. The probability of an event that is certain to occur equals 1. And if the probability is less than 0.05, we conclude that it is unlikely to occur. So we've got this range here from 0 to 1. 0 would be an impossible event, just creeping up to 0.05. Anything below that would be unlikely to occur. And then we have the probability would increase until we get to the probability of 1, or you can think of it as 100%. And that would be for an event that is certain to occur. We want to give exact answers unless we are asked to approximate. And please note that the earlier in a problem that you round or approximate, the less accurate your final answer will be. Therefore, we want to hold off rounding for as long as possible. It's often the very last thing that we do in a problem. Capital P, open parentheses, capital A. That denotes the probability of event A occurring. So one event here. Conduct a procedure and count the number of times event A occurs. Based on your results, the probability that event A occurs is approximated as following. Probability of capital A is equal to, hopefully you see this as a fraction. The numerator in this fraction is going to be the number of times event A occurred. The denominator is going to be the number of times the procedure was repeated. Another way to look at it is the numerator is the number of successes over the number of possibilities. Let's see an example. What is the probability of randomly selecting one student from this class who is wearing a hat? So pretending we were face-to-face right now, we would write that out as capital P, open parentheses, wearing a hat. That's the event we're looking to find the probability that it occurs. Close parentheses, equal sign, and then we're going to set up a fraction. Our numerator would be the number of us in the class wearing a hat right now. And our denominator would be the total number of students in the class right now, because that would be the number of possible people wearing a hat. Since we're not face-to-face, we'll just make up some numbers for that. So I'll use my morning class, for example. I had 40 students in my face-to-face stats class this morning, and I don't recall exactly, but I think there were about 5 of them that were wearing hats. So this would be the probability of randomly selecting one person from the class and them wearing a hat. 5 over 40 is a good answer. However, we want to give our fraction in the most reduced form possible. 5 and 40 are both multiples of 5, so we would take them down by a factor of 5. That would give us 1 over 8. So this would be a great way to state the exact answer. No rounding necessary, just 1 over 8. Now, I'm going to type that into my calculator, just on my phone here, because this is also equivalent to 0.125, and that decimal ends right there. So this would also be considered an exact answer. I didn't cut the decimal off. I didn't round or change anything about it. On my calculator, it says 0.125 and then it ends. So this would also qualify as the exact answer. Now, if you check your directions carefully and they say, please approximate to the nearest, let's say 2 decimal places, then we would take that and change it to 1, 3. Okay, so this one right here is an approximate answer. And if you're ever wondering which way you're supposed to submit your answer, just check right underneath that cell. It should be clearly written for us, for you in directions underneath the cell in which you type the answer. If it doesn't have any directions about please approximate to the nearest so-and-so, that means you're not supposed to approximate at all, and you'll want to give one of these 2 exact answers. All right, let's look at another example. When 3 children are born, the sample space is sample space. We open these with a squiggly bracket. Okay, this right here is called a sample space. Ends there. All right, 3 children are born, so this sample space, BBB, B is for boy, gender identified at birth, and G is for girl, okay? So BBB would be a family that had 3 boys. Here we've got a boy, boy, then a girl. Here we've got different 3 children born. We've got boy, girl, boy. We've got boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and then finally, if a family or 3 children are born and it's all 3 of them are girls. G, 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 girl, girl, girl. Okay, in this sample space, if you count how many possible outcomes there are, you'll get the denominator. So we have 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so this is called the sample space, and there are 8 possible outcomes. Assuming that boys and girls are equally likely, find the probability of getting 3 children of all the same gender. So we'll write that with a capital P, open parentheses, and what we write in parentheses here is 3 children of the same gender. This, whatever we write in parentheses, leads us to our numerator. So go back to your sample space and count. How many of these 8 outcomes have what's written in parentheses? 3 children of the same gender. Got 1 right here, 3 boys, and a second one right here, 3 girls. That leads us to our numerator of 2, and the total in the sample space leads us to our denominator of 8. Reduce that to 1/4, or write it in its equivalent decimal form, 0.25. Those are both exact answers. Section 4.2 is on compound events. So we're going to talk about 2 events or more, and we're going to need to use the addition rule to then add those fractions together. All right, if we have 2 events that are disjoint events, it would be written out as capital P, open parentheses, capital A, just like before, but we would write the word or, and then our second event, capital B. If there was a third event, we could write or, capital C. close parentheses, and that's going to be equivalent to, we just learned how to set this up. It's going to be its own fraction. And then we would write plus sign, or leads us to plus. And this right here will be the fraction for our second event. Now, if our events have the probability of existing at the same time, so therefore there's this overlap, then we have to consider those what we call not disjoint events. And what we can see in the formula is everything's the same until we have to subtract out the probability of event A and event B occurring at the same time. That's that overlap portion. Because what happened here is we counted it for the probability of A, but we counted it again for the probability of B, so it got double counted. So we just subtract out that overlap because it was counted twice. Now the multiplication rule is very similar, except this is used when we have the word and. So it'd be the probability of event A and event B occurring. If that's the case, we're going to multiply our probabilities together. Now, should our events' probabilities be independent of each other, then we go with capital P, open parentheses, capital A, the word and B, close, equal sign. This will be its own fraction, multiplication, and this will be its own fraction. But similarly to the addition rule, if our events are dependent, then we have to make an adjustment at the very end of the formula. So this all looks the same so far. The adjustment comes in at the very end right here. For this fraction, we'll be calculating the probability that event B occurs after event A occurred. If the events are dependent on each other, then once event A occurs, the probability of event B will change, and therefore we will have to set up this fraction after event A's occurrence. Here we have a finite set of outcomes, 50 of them, in a table for us like this. We've got, these are for test results. We've got 44 of them were positive test results, and we've got 6 of them were negative test results. Now, to use the multiplication rule here, we would check if without replacement is specified. Okay, so you'll look for that in the wording of the question. If it says without replacement is specified, then the events are dependent, okay? And that would mean that the numbers will count down. Let me explain. If we're talking about the probability of event, I'm going to call it P for a positive one, and the probability of, I'm going to call it N for a negative test result is polled. And in the question, it says that once we poll event A, we are not going to replace it. And then we're going to poll event B. So for this table, after we poll event A, which would be a positive test result, and we don't put it back, then we only have 43 positive test results left out of 49 now. So now when we go to poll event B, which in this case, we would want it to be a negative, there are 6 out of 49 available for us to poll. That's what I mean by the numbers count down. We're going to crunch these numbers with a more concrete example in just a moment. Let's start with an example using the addition rule first. Remember, addition rule, so adding, will happen when we're asked if event A or event B occurs. To do this, we need to get a little familiar with a deck of cards. Hopefully you already are, but if not, no problem. A deck of cards consists of 52 cards. 26 of them are red, 26 of them are black. 13 of them are hearts, 13 are diamonds, 13 are clubs, and 13 are spades. These are called the suits. There are 4 different suits in a deck of cards. And a deck of cards, you guys, is used often to learn about counting, statistics, probability, because it's a nice finite set that gives us a breakdown with all these possible outcomes. There are 12 what we call face cards. That would be the 4 jacks. You can see they have a face on them, the 4 queens, and the 4 kings. So a total of 12 face cards. There are 4 jacks, same as there are 4 aces. There are 4 twos. There are 4 fives, 4 sixes, 4 sevens, 4 eights. So 4 of each. There are 2 reds of every card and 2 blacks of every card. What I mean by that is there are 2, let's say, red twos. 1 and 2 of them right there. There are 2 blacks of every card. So you can see there are 2 black twos, 1 and 2. That's what these ones mean. 2 reds of every card and 2 blacks of every card. All right, now that we have talked about how a standard deck of cards is composed, let's try an example. A card is drawn from the deck. What is the probability your card is a king, queen, or jack? So we would write that out as capital P, open parentheses, A or B or C, A being queen, A represents the king being pulled, B is for the queen being pulled, and C is the third event, the jack being pulled. Now these are disjoint events because there is no overlap in these king, queen, and jack. No overlap, okay? There's no single card that could be a queen and a king at the exact same time. So since there's no overlap, we call them disjoint, which means there's no risk of us double counting anything, so no need to do that subtraction of something at the end. We're going to set this up as probability of a king, that will get its own fraction, plus probability of pulling a queen will get its own fraction, plus the probability of pulling a jack will get its own fraction. Numerator is identified by the count for the word in here. So there are 4 kings, and the denominator is the total possible, 52. There are 4 queens out of 52 cards, and there are 4 jacks out of 52 cards. Now you may be thinking to yourself, aren't we supposed to count down? Is this with replacement or without? That is for the multiplication rule. This is checking the probability of pulling one card from the deck. So it's not pulling a card and then what happens. It's you pull a card, is that individual card a king, a queen, or a jack? Okay, now we just have to remember how to add fractions, which requires a common denominator, and we have that. So our unit is 50 seconds, so we just add the 4s, keep our 52s the same. Let's show that work. 4, 8, 9, 10, 11, 12. That's 12 52s, which reduces to 3/13. So the probability of pulling a card from the deck and it being a king, a queen, or a jack is equal to 3/13. Kind of like it in the non-reduced form, because you can see that there are 12 out of the 52. King, queen, jack. If you count these, 4, 8, 9, 10, 11, 12 out of 52. All right, let's try an example where the cards are slightly different. A card is drawn from a deck. What is the probability your card is a 2 or a red card? Okay, 2 or red. Let me erase some of the scribble I have here. Eraser. I'm going to erase all this. Okay. I want to make it really clear for you guys that there's an overlap here. Probability that our card is a 2 or a red. So twos are here. 4 of them, okay? And the reds are here and here. So when we go to set this up, we have some cards that are going to be double counted. How many cards do you think of the cards that I just circled are circled twice and therefore will be double counted? I hope you said 2 of the cards. The 2 of diamonds is circled twice. It was circled because it's a 2, but then it was also circled because it's red. And the 2 of hearts is also circled twice. It was circled because it was a 2, and it was circled again because it's red. So these 2 cards are going to be double counted. So careful of that. At the end, we're going to have to subtract out these 2 out of the 52 because they will have been double counted. Watch, you'll see. So these are not disjoint events. You see the overlap. So when we set up the probability of event A or event B, we have to make sure to do the probability of A plus the probability of B and then subtract out the overlap, anything double counted. All right, it's going to look like this. Capital P, open parentheses, 2. The word or leads us to a plus sign. And then a red. So capital P, open parentheses, red, close it. Subtract out the probability of, and this is the overlap part, red 2s, okay? The red 2s. That's the 2 of diamonds and the 2 of hearts. Those are the red 2s. All right, each one of these is going to get its own fraction. Probability of a 2, there are 4 2s. So this one right here gets the 4 out of 52. Plus sign, probability of red, there are 26 reds. So the numerator is 26 out of 52. Minus sign, this count right here, there are 2 that were double counted. So we're going to subtract out 2 of 52. All right, we have the same denominator for all of them. That's nice. So we just have to do the operations in the numerator. 4 plus 26 is 30, minus 2 is 28. That reduces to 7 over 13. So the probability of pulling one card from the deck and it being a 2 or a red is 7 out of 13. Okay, now to an example using the multiplication rule. Multiplication rule is used when not the word or, okay? If you guys see the word or in your directions, like find the probability that this or that, if you see it in the directions, find the probability of this or that. For this, you use addition, okay? Don't use the multiplication rule if it says or. We want to use the multiplication rule if the directions say this event and that event. Another way to say it would be both events. This is the same thing as and. Another way to say it is all of the events occur. These right here are all ways to say one event occurs and the other one occurs and the other one occurs, all the way up to and all of the events occur. So pay attention for these keywords, and, both, all. Let's see an example. 3 different people are randomly selected from your class. Find the probability that they are all born on a Monday. All. That makes this a multiplication rule question, okay? Give your answer to the nearest thousandth. All right, so we are going to be selecting 3 at random, and we're looking for the probability that they are all born on a Monday. These are independent events because the probability that one person is born on a Monday does not change the probability that someone else is born on a Monday, okay? Days of the week of births are independent of each other. So we would set it up the probability of, open parentheses. Now we're selecting 3 different people. That's why we see A and B and C. This represents all. Now we're going to apply the multiplication rule this time. I like to think of it as the and signs turn into the word and turns into a multiplication, just like before the word or turned into a plus sign. All right, this probability of A is going to be its own fraction multiplied by a second fraction multiplied by a third fraction. All right, so let's set these fractions up. The probability that, and this A right here represents a person is born on a Monday. Well, there's a 1 out of 7 probability that the first person we talk to is born on a Monday, because there's 1 Monday out of 7 days in the week. Then the multiplication is here. This next 1/7 comes from here, the probability that a person is born on a Monday. It's again 1/7. And there is a third fraction, because we're talking about 3 different people, and the probability that that person is born on a Monday, so multiplication, is also 1/7. No adjustment in the numbers, no counting down, nothing like that, because these events are independent of each other. Now we just have to remember how to multiply fractions. Okay, unlike adding fractions, we do have to multiply the denominators. We have to perform the operation on the numerators and on the denominators. 1 times 1 times 1 is 1. 7 times 7 times 7 is 343. If you're asked to give that to approximately 3 decimal places, which we were, give your answer to the nearest thousandth. Thousandths is 3 decimal places. Then we would write it as 0.003. Okay, let's look at an example without replacement so we can see how things change here. This is going to be dependent events. 50 drug test results are given from people who use drugs. If 2 of the 50 subjects are randomly selected without replacement, to the nearest thousandth, find the probability that the first person tested positive and the second person tested negative. This is the one that I had started to set up for us. Let's finish working it out. So these are dependent events because the word without replacement. Once that first drug test result is pulled, it doesn't get put back in. So the second event occurring will depend on the new numbers. Okay, so we're going to change probability of A here. The word and becomes multiplication, and the B becomes probability that event B occurs after event A already occurred. So we got to take our time with this second one for sure. Okay, probability that event A occurs, we know is 44 out of 50. And then that's multiplication. And the probability that event B occurs after A is 6 out of 49. Where did those numbers come from? Okay, this was the table before event A occurred. Then once event A occurred, a positive test result was taken out, leaving us with 43 positive, 6 negative, and a total of 49. So with the new table, the new counts, the probability that event B occurs would be 6 out of 49 now. That's the counting down part. Multiplying our fractions together and approximating to the nearest thousandth as requested, we get 0.108. All right, I have 3 examples for you to try, so I would like you to pause this video and try them now. Welcome back. Let's see how you did. Let's just go straight for the answers first, and then I'll show you how to get them, in case you are having any trouble. Oh, darn it, I want to show you the answer first. Okay, well, the answer to number 1 is right here. I'm going to write it like this. 1 out of 133,225. The correct answer for number 2 is 1 out of 365. And the correct answer for number 3 is approximately 0.77. So these are the correct answers. If you got them without seeing my work, great job. If not, I was gonna then show you how to obtain them, but my work showed up before I could get there. So probability event A, 1 out of 365. We're going to multiply that by probability of event B, which is also 1 out of 365. You can see the result there. Here it changed because we're looking for the probability that they have the same birthday. These look very similar, but the difference is in number 1, we're being asked the probability that they're both born on November 24th. So our first fraction was 1 out of 365 because that's the chance that they're born on November 24th. But here it doesn't say born on November 24th. It just says that they're born on the same birthday. So our first fraction, whatever day the person says, is considered a success. So we have 365 out of 365. Doesn't really matter what they say. Here it was specified. It had to be November 24th. Here it's not specified, so anything they say is fine. Then the probability that the next person says the same birthday is 1 out of 365. So these are similar. I've heard it called the birthday conundrum, but the results, the probabilities are quite different. Similar question, very different results. And number 3 is changed up on us. You might think, oh, that was the same as the question from the last slide, but I switched it up in the wording right here. I asked you to find the probability that the first person tested positive and the second person also tested positive. So for this one, it's different than the last one because I was looking for the probability that it's positive, and then the next one is also positive. And we have to do this without replacement. So after the first positive result is pulled, that gets us our new counts of 43 and 49. So when we set up our second fraction, and that is again dependent on another positive being pulled, it would be 43 out of 49. So very similar to the example on the last slide, but look carefully at what's determined a success, or what goes inside the parentheses. Here it is first person test positive and second person test positive again. All right, that will finish our discussion on chapter 4, sections 1 and 2. My name is Emigh, and I will see you next time for our discussion on section 4.3, which is titled Complementary and Conditional Probability.